Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in the University of Helsinki in Finland, and I study the universe. That means that I'm a theoretical physicist who specializes in cosmology. I'm messing up my whole intro today. And yeah, I am a cosmologist. That means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically everything happening inside the universe. And as some of you have noticed, I am on late today, 5 minutes late. I do apologize for that. I had a bunch of technical issues that resulted in me changing laptops just before going live. So it's been a bit of an off-screen chaos going on here, but we're ready now. We're all set, and the delays were absolutely on my side this time, but we're all set. So, as I said, I'm a cosmologist. I study the universe, and there's a lot of stuff to study in the universe. And today we're going to go back to the very, very, very early part of the universe, some of the earliest things we know about in the universe. And this is a broad topic. This is not something I'm going to cover alone. So joining me today to help me talk about this is Lorenzo. Hi, Lorenzo. Welcome to Cup of Cosmology.
Hi. Hello.
Do you want to introduce yourself to people?
Yeah, I work in as a student, so I'm a support. So my transition in the early universe, especially what but unfortunately today, I don't know if I can give this about my research. Probably it's gonna be a bit. How much deep can I go in my?
Well, let's start with the basics. So, for anyone who didn't hear that, Lorenzo is a PhD student working in the same institute as me and working on phase transitions in the early universe, which some of you have probably already heard about, and inflation, which is going to be the topic today. So, just want to say hello to everyone here. Hi to Ange, hi to Scott, hi to David Howden, David Dunn, all of the regulars. James, nice to see you as well. Great to see everyone here. Really nice to see all of you coming in. I know there are some audio issues again, apparently. I'm really not sure what the problem is because it's on neither of our sides. We've tested it and everything seems to be working perfectly fine for both of us. This is why we changed laptops and did everything beforehand. So if there is a slight audio issue, I apologize for that. I do think there is a problem with Restream. And I'm going to try to get this fixed, but currently we do the best we can. So, hey, Hemza, great to see you as well. So nice to see all of the regulars joining in again. So Lorenzo, do you want to just set the scene? Can we get a brief, like 2 sentences description? What is inflation?
Inflation is a period of accelerated that is used to explain the temperature that we see in the column. This is probably the most brief give of it.
Yeah. When we say it simply, as you just said, it's this
with my explanation we can go more.
Yeah, it's definitely a good starting point, right? It's this brief period this period of exponential expansion in the early universe. As David Dunn is just saying here in the comments, please do like this video, subscribe to the YouTube channel if you haven't done so already, leave a comment down below, do all of the usual YouTube things. If you're watching on Twitter, that's awesome too. Feel free to head over to YouTube and join the conversation. So yeah, I actually do mute my mic when the guest is talking. Always, it doesn't help. But thank you for the tips here. And hey, Paul, great to see you on a train with spotty internet. Well, Paul, if you have audio issues, I'm going to blame your spotty internet and not us. Okay, so Lorenzo, you just gave this brief overview of what is inflation, a very nice 2-sentence summary. So jumping off of there, this period of exponential expansion, how long ago are we talking about here when we say exponential expansion in the early universe? Like, is this something from yesterday or how long ago is this?
It's a bit farther than yesterday. To be honest, we don't know how much farther. There are no experiments on inflation. What theoretical physicists usually do with energy scales. And the 15 GeV, or at least we assume started at that period of time. Know how long it lasted. There are constraints on the length of inflation lasts for long enough in order to that we see in the universe today, but pretty weak so far. So there's much to do. I think in terms of it is as old as they, so is 13.8 more or less universe that describes this fraction of seconds old, like 10 to the second, something like that. So we're first stages of the universe.
Awesome. So as Lorenzo was just saying here, I'm just recapping just because of the audio issues, just to make sure that everyone hears everything. So you made a really nice comment here. So I asked how long ago was inflation, and Lorenzo gave the answers. We really don't actually know because it was a trick question. So we know that inflation ended about 13.82 billion years ago, as Lorenzo was just saying, but we don't know when inflation started because we don't know how long this period of exponential expansion lasted. We have lower limits. It can't have lasted less than this particular amount, or the universe would look different. But we don't have an upper limit. And I heard somebody once phrase this as inflation deletes the memory of anything that came before. So inflation could have lasted billions of years and we would have no idea. So we just take inflation as the starting point from which we develop everything else onward. So inflation is like our ground zero where we go forward from. But we don't know how long inflation lasted, which means we don't know when it started. But we know that inflation finished 13.82 billion years ago. So before we jump, and we actually have an image to show this, so we can bring up an image here, which if I remember how to bring up images, because as you've seen, I had some technical issues at the beginning. We have this image of the history of the universe. Now, oftentimes here on the show, we talk about the CMB, which is this thing 380,000 years after the Big Bang. But now we're going to the left side of this image. You'll see there's this period here labeled inflation. And that's what we're going to talk about today. When the universe, you see in this pictogram always, we show the universe as being this point, and then suddenly it grows dramatically. And that's our launching point for today. So before we jump into stuff, Lorenzo, is there anything else you wanted to tell us about this image? Because I know you wanted us to show this.
I think it's good to keep in mind the picture because there are so many informations here. But at least in this blue greenish surface, the picture is called recombination. This is what cosmology is called, and this is going to be a very important period for us. Basically, through the expansion universe, the universe starts from being hot plasma to expand. Recombination is exactly that plasma is like enough such that photons free stream to run freely without. It's basically the earliest period of the universe that we are able to see. So whatever is before that is damped, is affected. So this is gonna this is all I need to say.
Yeah, so obviously everyone who's watched this show more than once, or at least once, knows about the CMB, the cosmic microwave background radiation, because I'm incapable of going more than 10 minutes without talking about the cosmic microwave background radiation. But as Lorenzo was just saying, this is the oldest light we have. So anytime we're trying to look at stuff before recombination, light becomes something that we can't really use properly because, light kind of the CMB is the earliest we go. Now, of course, if any of you have joined in the gravitational wave streams, we can use gravitational waves to go earlier. But even though it came a long time beforehand, the CMB does tell us a lot about inflation as well. And we are going to get into that. But I just saw there was a question there by James saying, we analyze inflation by light spectrum. Odd question, is there anything that can change the wave of waves other than time? So I'm not sure what you mean there about what can change the wave. So light as it travels throughout the universe is going to be redshifted, it's going to be stretched. But also if a photon particle of light gets absorbed by a hydrogen cloud, it's going to change slightly. So there's a lot of processes in the universe that can change the wavelength of light or change how it's behaving. But most of the photons from the CMB don't have enough energy to do much else. So the only things that really affect the light coming from the CMB by now are gravitational effects and very, very, very dramatic processes, but overall, and redshift, so the expansion of the universe. But overall, we don't really need to worry about the photons being disrupted too much, at least the CMB ones. Comment from Paul here: if the universe is infinite and uniform, then both before and inflation, it was just as large, but a lot more dense. Yeah, it's always a question of what came before inflation, and that's not what we can actually answer. So we are going to, so just to give everybody an idea of where we're going today, because I've been told by some of you before that you like to have an overview of what we're going to talk about. So we're going to start by doing some background information, which we already are doing here, just some basics about inflation. Then we're going to discuss why we need inflation. Lorenzo's prepared some really cool sketches that we're going to use to walk us through why we need inflation, how inflation helps us address some issues that we have. Then we're going to talk about what could possibly, how does inflation happen? Why doesn't it last forever? Then we're going to talk about basically how we connect inflation and the CMB. So I think that's kind of the picture for today. Do you agree, Lorenzo, that that's the big roadmap of today?
Yeah, I agree.
Awesome.
I also wanted to add that you read before, like inflation, because it's something that I was asked. And I think, like as you said, it's something, but I want to ask, not physical, like I think, like you can answer in a philosophical way, like what is physics? The point of view of physicists is some. We have a universe this way, and our role is to find to. But we don't have the answer for the things are happening. We just want to, or we explain how they are happening, not why. Is something that is unphysical in a sense that we period, and since we cannot have access to that model, how it works, or we don't have any, so that kind of period is beyond the physical questions. I think it enters questions or religious questions. But okay, this was just
no, yeah, I think it's a good point to make, because these questions like what came before inflation is like what came before the Big Bang, what came before time. They are questions that, as Lorenzo was saying, we don't really answer from a purely scientific point of view, because we don't have theories or models to answer these questions. It's not what we're trying to do. So these questions take us into the realm of metaphysics. And it's what I always say, metaphysics is fun to chat about over a beer or over a coffee, but it does move beyond what we normally work on as scientists. So jumping in, before we get into inflation, we wanted to mention some background knowledge that we need. Lorenzo wanted to talk about causal contact, and we have a cool sketch for that. So Lorenzo, do you want to tell us what we mean by causal contact?
Yeah, as Diana said, to understand it's crucial to understand what it means. Here I drawing is very bad, but I patches of the universe, I call them. And what it means for the two patches of the universe, it means that in a sense they can exchange information. Is this possible? Is that are separated by a distance of time. One of these patches, say A, signal to B. At the beginning, these are disconnected in the sense that this light didn't have enough time to reach. If a light signal doesn't have time to reach the other, that they cannot exchange information, because information can travel at least, at maximum, at this what general relativity or special relativity. So causal contact that happens signal has enough. If we wait for long enough, this is gonna arrive to the patch B, and on. We will say that these two patches are causal, such that they can share information. This is our definition of causal connection. Here is too vague ask, and I can be more specific on that.
I think your explanation there was very clear. So just to recap to everybody here, just to make sure, because causal contact is something important to understand. So as Lorenzo was saying, we know that light in the universe does not travel infinitely fast. It travels at the speed of light. This means there is a limit for the distance light can travel in a given time. So if you have two patches of the universe that are very, very, very far away from each other, it might be that they haven't yet had time to exchange information or to exchange light. And at this point, we say they're not in causal contact. So something is in causal contact when it has had time to share information. So if you have two patches of the sky that are close together, you would say they're in causal contact because they can exchange light beams or information. We know that information travels maximum at the speed of light as well. So if two patches are very, very distant, we say they are not in causal contact. So if there are any questions about causal contact, now is the time to ask, because this is something that is important to understand before we go forward. Leave it there, as always, put all your questions in the comments, questions in the chat, whatever questions and comments in the chat box. We will try our best to answer all of them, as always. And as always, if you make jokes, you will completely derail the stream, but that's perfectly acceptable too. So any possibility that the speed of light could have been different in the early universe? I love that question. What do you think, Lorenzo? Could the speed of light have been different at different times in the universe?
Light been different. I think speed of light cannot be the of massless particles. From a theoretical, this is a problem of symmetries. This massless particle, I think the nature of particle doesn't with the temperature of the universe or with the age of there are other signals that can be like gravitational waves. Gravitational waves is allowed to change speed in the early universe because there are different mechanisms to generate light or photons that are by the I think it's not possible.
Yeah, so to the best of our knowledge, the speed of light. Hey, Abyss, great to see you in the comments. Haven't seen you in ages. Really nice to see you, Abyss. So yeah, as Lorenzo was just saying, the speed of light, we're pretty sure has been constant throughout the history of the universe. So we don't think it used to be different and then it changed. Gravitational waves, as far as we know, also travel at the speed of light. But there are a lot of people working at trying to figure out if these constants, like the speed of light, could have been different at different times in the history of the universe, because that would be very important to know. But currently, we don't think the speed of light has been different at any point in the universe. We have another question here by David Howden now of, does it require light to actually travel between them to be in causal contact, or just near enough that light could have traveled? So you don't actually need them to exchange information to say they're in causal contact, just that they have the potential. But as soon as you have two patches of the universe that are close enough, they will exchange information. So they're not necessarily sending light beams back and forth. But for an example, the temperature is now close enough that it can influence each other. So this is what we mean. As soon as they are close enough that they can exchange information, there is an exchange of information, even if it's not directly light beams going back and forth. I see we have Ali here watching us as well. Not surprising. Let's see. Comment from Paul here. Does causal contact also apply to other light speed types of effects like gravity, magnetism, other things? So I think, as we were just saying here, this is really not just light. When we're talking about causal contact, it really means they can exchange information. And the case we are going to be using later is temperature. Oh, we've just lost Lorenzo. Let's see if we can get Lorenzo back. Don't know what happened there. So keep on going till Lorenzo comes back. So the one we're going to discuss later on is temperature. So we'll talk about patches of the universe that have had enough time to exchange temperature information, so the temperature can affect each other. But when we talk about causal contact, so magnetism travels at the same speed as light because it is part of the electromagnetic force. Gravity also travels at the speed of light. So really, causal contact just means we have patches of the universe that can exchange information amongst them. Let's see if we get Lorenzo back. But not sure what happened there. Have to see when Lorenzo reappears. Okay, Lorenzo, we do not see your video or audio, so I'm not sure what's happened, but you say you're here, but we do not see you or hear you anymore. So not sure what's happened there. Yeah, let's see. Getting it back, sorry everyone, again, technical issues, always happens. We always get technical issues. But we do not see or hear Lorenzo currently, so let's see if we can fix that. Okay, in the meantime, while we try to get Lorenzo back online here, a few more comments. Speed of light is constant, but if light is traveling in a void opposed to a gravity-heavy area of universe, must be slower to exchange info. Okay. Just trying to figure out the issue here. Sorry again for the technical issues. Okay, so Lorenzo just experienced inflation. Yes, that does happen sometimes. Just technical issues happen sometimes. So yeah, the speed of light is constant. Now, when light travels in a vacuum or through a place where you have a lot of things happening in the universe, it still, to the best of our knowledge, travels at the speed of light. Now, it does slow down if, for an example, it travels through a medium, and we do have Lorenzo back now. Don't know what happened there. It looked like you went to type something, and we just completely lost your video. No worries, you're back now.
Yes.
Random issues that happen.
Something?
You didn't miss anything. I'm just going through the questions here. We have quite a few interesting questions. So we were just discussing what James says here about if the speed of light is constant, or if the speed of light changes when you're in a void versus a region where you have a strong gravitational force. The answer is, to the best of our knowledge, no, but some people are working on that. Light, as far as we know, only changes speed if it travels through a medium that is not a vacuum. An example, light through water travels slower, light through glass travels slower, but in a vacuum it always travels at the same speed. Okay, some comments here about, do we need...
I think the question is...
Go ahead, Lorenzo.
It's true, as you say, it's true that the light doesn't change. But probably, or I don't know if, like in presence of the strong field, light is so that doesn't change the energy. Or
I would say if light is traveling through a magnetic field, then it would be deflected, but it shouldn't slow down. Okay. Yeah, I think if it's traveling through a magnetic field, it would only be deflected. Of course, if it's traveling through a medium like light or water, then it does slow down. And as David Dunnish was saying in the comments, you and I are now back in causal contact, which is good. Okay, so hopefully now the idea of causal contact is clear. We have the example here. Lorenzo disappeared from my causal horizon and then came back into the causal horizon. So now we can move on to why we need inflation. And I'm just going to preface this by saying, we have the hot Big Bang model, which is the best model we have to explain the history and evolution of the universe. And it does a remarkably good job of explaining a lot of things. But let's see a few more comments here. One from Ali: traveling through a varying gravitational field should change its frequency. Yes, it would change the frequency, but not the speed, I believe, right? The speed of light should always be the same. You change the frequency, you will change the wavelength, but the speed should still be the same. That's how we get the redshifting.
Yeah.
Comment here. Go ahead, Lorenzo.
Yeah. Maybe because if you, for example, fall in speed of light, what the observer sees outside the black hole, for example, or you see a slowing down, but doesn't mean that it's really you see it slowing down. It's actually proper speed. But I don't know if this is what but it's a question and probably needs an hour to answer.
Yeah, so this is an excellent point. When you go into a black hole, stuff gets weird and light distorts. But as far as we know, it still travels at the speed of light. As Abyss says, if only we could measure the cosmic neutrino background someday we would get there, hopefully. But now back on topic. So we want to talk about why we need inflation. And there are usually two, potentially a third problem. So I was just saying the hot Big Bang is really, really good. We like the hot Big Bang model, but it has a few issues. And the first issue is what we call the horizon problem. So Lorenzo, do you want to tell us about the horizon problem? And I'm going to bring up your sketch for this.
Yeah, if I have time, I like to present funny, because this is how it. This is horizon problem. The problem is in and have to on the right of the room. And these two heaters are completely the way to turn them on, independent from the other. Turn on the left one, or some that is turning some battery that is turning on the heat one that is turning on the heater from the right. And I to measure the left from the one on the left and the one on the right myself. What is these two heaters are set at the exact same and very low because these two heaters are so it's very likely they are set at the same temperature because they talk to each other. What's happening here in the universe? In this picture, I drew a Lorenzo in the middle of this is a picture of my. There's one eye, another eye pointing to the left. Is a metaphor for an experiment on the, and I do this surface that, as you see, scattering surface. Telling you before of the universe. The meaning is that what I can see from this is. So the point to the right, I look to the left, coming to me from, and I measure photons have the same temperature. These two regions of the universe are way to be causally connected. The moment these photons are generated at the same scattering surface, so the light travels, but I'm in the middle of it. I'm in the middle regions. So before the connection, these two interact with me. So the light ray from the left and the right arrives to the other patch, causally connected. And they ask how two regions that are not causally have the same temperature. Why I get the same information from these two patches being causally disconnected. This is what we call horizons. To be no reason for these two patches to join the same temperature. In terms of photon is energy comes from the left and the right, they have the same. Why or how do that? First problem.
Yeah, so I think that's a really nice explanation there. So I like the analogy of the heaters. So just recapping this, if you're in a room and you have two heaters on opposite sides that have completely different thermostats or systems, you can set each one to very different temperatures. And then if you measure the temperature of both, they're likely to be different. Now, what we have here in the universe is if we look at different patches of the night sky on the CMB, we know that the CMB has these temperature differences, but overall, there is the same temperature. So in fact, let me just bring up the right image here. So while we know that the CMB has hot spots and cold spots, this amazing picture here, this cosmic microwave background radiation, oldest light in the universe, amazing picture. Now there are temperature differences, but these are of the order of 10 to the minus 5 Kelvin. But overall, every patch that we look at here is at 2.73 degree Kelvin. So it's really, really, really remarkably close temperatures here. The horizon problem, as Lorenzo was just saying, is the question of why are these patches at different temperatures? And using the analogy of the heaters, if you have the heaters at different parts of the universe, and these heaters have no way of talking to each other, you would not expect to get the same temperature reading from these different places. And people really like your sketch here. Someone's saying Michelangelo drew it to explain expansion. So your sketch has just been compared to Michelangelo's drawing. So you should take that as a very high compliment there. But I do like the analogy here of the heaters, and this is really what we know as a horizon problem. So looking at the CMB, how do we find these things that are at almost the same temperature if they haven't been in causal contact? This is the first problem, and we're going to come back to this in a minute with some more diagrams and more explanations when we solve the horizon problem. But now there's another problem we can talk about, which is the flatness problem. So Lorenzo, do you want to tell us about the flatness problem?
Yeah, it's more difficult because it's a problem that is physical. It's more about we call them naturalist problem, tuning of some good way of explaining the problem is of the units. So let's do that. We can model the universe in three different ways. We say that our universe has a curvature being here. This omega refers to what we say of curvature. Be as a positive curvature as a sphere. We say that it has negative curvature in hyperbola. In these two different cases, there's a limit in the case of zero curvature, one in this picture, flat case, where the universe We have numbers instead to be flat. Why is it unlike? We have the possibility for the curvature. We have a whole real number. The curvature can be a number, every real number from minus and flat specific case where curvature is zero. So it's zero for us. It's a very specific, likely situation. So here is us a bit. But what with inflation? The thing is that today will be approximately flat, not flat, with a good approach. And besides being very it also leaves us possibilities because it's close to zero, but not exactly. Our measurements are not good enough to discriminate between all the windows open. Is that if were so if the density in the curvature was smaller than 1, or what will be the age actual size, the size that the universe has to calculation, you end up is 10 to the minus 11. But we know that the universe is older than, so cannot be open. Say, okay, so what is close? Or to have positive curvature. Assume the universe is positively, then what happens is that, I don't know, if some of you already heard about it, expand, and then it's called what we call bound. And the time for it to expand again is 10 to the, but our universe for minus 40 seconds because we are all Platten's problem is this problem is so old. One openly curved host doesn't allow that. The only possible way, but flat, is a very unlikely situation. So this is problem. It is a state in the both ways.
Yeah, I think that's a very nice explanation there, Lorenzo. So, as Lorenzo was just saying, the curvature of the universe, which we parameterize with one number, could be anything from minus infinity to plus infinity. If it's a negative number, we'd have a closed universe. If it's a positive number, we'd have an open universe. And we just so happen to be in the case where we have zero curvature, which does seem a bit unlikely. Of course, you could answer the question, as some people do, of maybe, would we say it's unlikely if we got any of those numbers? There could be thousands of different ones, and we just say, oh, this is an unlikely case. But also, as Lorenzo was saying, currently we don't have exact measurements. We can't say the curvature is exactly zero. But based on our measurements, it appears to be very, very, very close to zero. Which again, given that it could take any possible value, the question of why is it close to zero is what we call the flatness problem. Then there is a third problem. So we have the horizon problem, we have the flatness problem. And there is a third problem that is not discussed as much, but is actually one of the early motivations to propose inflation. And this is known as the monopole problem. And I'm just going to give a quick explanation because we're not going to go too in detail with the monopole problem. So there's a lot of, we know that there are four forces in the universe: electromagnetic force, gravity, strong force, weak force. If we go back to the early universe, we know the electromagnetic force and the weak force were joined together. And then you can ask the question of, can we put the strong force in in which case you'd have what we call a grand unified theory. And then can you add gravity and have a theory of everything? Now, in these models of grand unified theory, there were a lot of ideas thrown around. And a lot of these predict what are known as monopoles. So if you consider magnets, we know magnets have a north and a south. They have the dipole here. You cannot have a north or a south. You always have a north and a south. If you cut a magnet in half, both halves will have a north and a south. But a lot of grand unified theories predict that we would find isolated monopoles, so just a south or just a north. Now, this is something we have never observed. And this is also the question of, why have we not observed these? Of course, you could say maybe none of the grand unified theories are correct, but this was one of the motivations to try to find an explanation for why monopoles don't exist. So, 3 problems to the Big Bang model: horizon problem, flatness problem, monopole problem, if you believe in the monopole problem. And people already realized many years ago that a way you can solve all of these 3 problems is if you have a period of exponential expansion in the very early universe. In order to solve these problems, you need a certain amount of inflation to take place. This is what we were saying before, that we have limits on lower limits, like we need at least this amount of inflation, but we don't have upper limits. So let's suppose now that in the very, very, very early universe, the universe grew exponentially. Like we went from having this really, really small, hot, dense thing to having a really, really big, hot, dense thing. Slightly less hot, slightly less dense, but it grew exponentially. So, Lorenzo, how does inflation solve the flatness problem? What does it do for us to fix the flatness problem? Going to do that one first, then back to the horizon problem.
This year, to understand how inflation solves the right, understand why it also the flatness problem.
Sure, let's start with the horizon problem then. So how does inflation solve the horizon problem?
Share this one. Yeah, exactly. This picture. First, it is what is horizon. We distinguish horizon, and horizon is the universe that is causally connected with us. Is a patch distance that comprehends the connection with us. And here in this, I draw in this horizon. I draw automatic way all the universe. You see that, or not the universe, like patch. At the beginning, before, or at least like without, I have horizon that is more, and through time grows like after the years than the universe. And so at some point, let's say today, horizon will have the same subpatch of the universe. And observation, let's say myself in the same, and as before, in the screen, there is a parameter u, I look left, and I see the same in this analysis patches of the universe connected. The problem here is that the faster than the universe. So horizon that is smaller, the actual universe, and time goes, the universe. And when I do the math, I'm expecting to see that the same time because of this, because faster, and that at a certain because the universe is to a period where the opposite, the actually grows faster, and this equation. I start from the horizon larger than this. So is inside the horizon to measure. Is inside the horizon. Inside the horizon, this universe is already, and is the difference with what was I was trying to measure. It wasn't causal. I start from the opposite universe that is already causal. As time grows, faster than the horizon measurement. I see the horizon being large is what happens today. We know that in the universe. But I measure that they were inside time before. They were causally connected before. If there is this when the universe in the horizon, then in the sense that this patch I see today, when I was telling the problem is that I was thinking that these patches for the first time when they reached this scenario, they had time moment to interact. This happened during inflation. This.
Yeah, so I think that's a really nice explanation there. Sorry, I wasn't sure if you were finished there. We have a bit of a lag, so it's always hard to see that we're not interrupting each other there.
Yeah, this is the problem. And I think comes straightly from problem from this. If I have an accelerated expansion universe, is, as I was saying, faster than the horizon. Or almost exponential expansion. If you take, for example, and you inflate this, you inflate a lot this sphere, or you take an hyperbola and inflate a lot locally, the effect of the curvature is you will start realizing curvature. So in a sense, the more this unit, less the effect of curvature. In a sense, this flat universe. The question is a bit more important when you put it. So of course, it becomes a bit difficult. The idea more or less is, and the inflation problems or this mechanism, in a sense that the monopoles, actually, that in there are no monopoles at all, or there is a lot of creatures, monsters that you can, which involves phase transition. There are a lot of different things. This is the idea, I guess.
Yeah, so we can recap this a bit here. There's a lot of information there to take in, but it's really, really cool physics. And I think the sketches you did really illustrate what we're talking about here. So we need to consider we have basically two different horizons that we're thinking about, the causal contact and the actual horizon of the patch of the universe that we're then going to be concerned about. Now, as Lorenzo was showing in the first sketch, the problem is that, if your patch is bigger than the causal horizon in the early times, this is going to be the case later on as well. And this leads to the horizon problem. However, with inflation, we introduced the idea that at some point in the very early universe, everything was in causal contact because everything was much, much, much smaller. Then we had a period of exponential expansion, so the horizon grew exponentially. This means that today, this patch that was in causal contact is essentially larger than the actual horizon of the observable universe. So everything within the observable universe, which is just a part of the universe we can see, was at some point in causal contact. So inflation offers us this mechanism whereby in the early universe, everything was actually in causal contact, and then it expanded so dramatically that now everything we see was at some point in the past together and now is very far apart. So then if you take patches of the CMB that are in very different areas of the sky, they were actually all together in the very, very early universe. They could exchange information, so they could balance out the temperatures already in the early universe, or the quantum information, which then led to the temperature later on. So we can solve the horizon problem by having this period of exponential expansion in the early universe. As Lorenzo was saying, this naturally leads to an explanation to the flatness problem as well, because you're pushing the universe out exponentially and you basically accelerate away any curvature. So any curvature that might have happened in the early universe, this number that we said could be anywhere between minus infinity and plus infinity, whatever number you start with, if you have a long enough amount of inflation, the universe grows so much that it's basically driven to be flat, regardless of the starting value. In a similar way, if you have this exponential expansion, any monopoles you might have had earlier on get diluted away, so we would not observe them today. So this simple mechanism of a period of exponential expansion can naturally solve the horizon problem, the flatness problem, and the monopole problem. And I know that's a lot to take in, so do feel free to ask questions. And I realize we've been ignoring questions for a while, so let me go back. Abyss, I know you had a super complicated question, as always, about transport equations of photons. I am not going to answer that live, but feel free to message me about that later on, because that's a cool question that we're absolutely not going to go into now. So when we introduced the flatness problem, we had a question from Scott of when we're talking about the universe being flat, how does this kind of work when we know that gravitational objects bend space-time? And when we're talking about the universe being flat, we're talking on large scales. Now, the thing is, galaxies are small. Clusters of galaxies are small when you think of the whole universe. So if you take a step back and consider the whole universe, of course, there's going to be regions where you have different types of curvature. But on average, the universe appears to be flat, as David Dunn then replied to that in the comments as well. As Abyss says, monopoles are hard to detect. Yes, so just because we haven't detected them doesn't necessarily mean they're not there, although they would manifest in the CMB. So about the donut theory, the idea that the universe could be shaped like a donut does not work with the idea that the universe is homogeneous and isotropic. It would be nice, right, if the universe was shaped like a donut. Then you could have a Pac-Man effect of going around.
Yeah, I'd like to be.
Yeah, it would be fun, but unfortunately, so we know that the universe is homogeneous and isotropic, which means it looks the same in every direction you look from wherever you are. This would not be true on a donut or a torus. More comments here. Yeah, there's a comment about the CMB from David Dunn. We will get to that. We will definitely get to that. Has anyone pointed out that Lorenzo looks a bit like Davey 504? I don't know who that is. So no idea. Apparently you look like someone. Well, we're always perturbing. So yeah, you look like someone. Good to know.
Is it French? I'm Italian. I wish it's not French.
Yeah.
It tells me I'm French. So.
Okay, and yeah, as David Dunn is saying, not everything is donut. Simpson was indeed wrong about that. Okay, so hopefully we've convinced you that, if we have inflation, the universe was in causal contact in the early universe, grew exponentially. This naturally leads to a solution to the horizon problem, the flatness problem, and the monopole problem. He's an Italian bass player. Okay, you look like another Italian, apparently. So, he's not French, so you're happy. We were going to talk about how we generate inflation, but given that we have almost been on for an hour, we are going to skip that and instead jump directly to the next point, which we wanted to talk. Yeah, we're almost at an hour already. So let's skip the whole thing about slow roll. We'll leave that for future conversation. But I do want to go back to the idea of the connection between the CMB and inflation. Because apart from solving these three problems for us, inflation does something else for us, which is really, really cool. So I flashed the CMB before, and I told you, it's at approximately the same temperature, but there are these tiny temperature differences. And the cool thing is that inflation gives us an explanation for these different temperatures. And I'm going to bring up another sketch of yours, Lorenzo, and can you maybe just walk us through what this sketch is and what it is showing us? So this is about things being sub-horizon, super-horizon. What is this? What did you want to tell us with these sketches?
Okay. Yeah, this one after a slow roll. You see this phi. As the let's try to skip. Let's just say that we have a component of the unit field that we call phi in the that realizes inflation. That how to generate inflation. Less perturbations or fluctuation, a scalar field that I call phi. In a quantum world, you can say that this scalar field oscillates around, and perturbation or oscillation scalar field propagates like a wave. I drew these three scenarios of how the wave can propagate. We say that these sub-horizon are very, very fast, Side horizon, there are many peaks. In this situation, field behaves quantic is a quantum regime. Determine the value of the field that depends where we observe, because oscillating very fast. This is the case of super, the case where there are no causal horizon. In this case, classically, in the value, which is its mean value, at any time, at any state, do my measurement, obtain the same result, the same measure. So this is classical regime. And the case in between horizon crossing, where I have exactly one period of oscillation, my horizon, my causal case, is when I can realize when the fluctuation of the field influences my measurement. I get completely random number. I get always the same number, depending where I measure file. I can profile of the fluctuation. So what happened? Before saying what happens, it's worth to say that expand because there is a causal horizon, the universe, like what is our actual horizon, and they through the history of the universe expand. They expand causal horizon. What space? The space is a stretches with the so it's not the causal effect, the wave, but is the like if you look at the space, is the grid that is expanding, and the wave is attached to this stretching with the grid. Is that during inflation, perturbation, and let's say a perturbation that in our actual universe, sub horizon, it causal horizon is large that we want to measure. What the actual universe than the causal horizon. This length gets and at some point horizon. So what happens is that if our fluctuations behave once the horizon, it behaves classically. This moment goes depending on the time when the crossing have the value of the field in a different point, behaving quantically oscillation of our field, constant value. But to stop, the quantum determines the value of through all the. So the moment I stop is crucial to my field phi. Or the thing is, patches of the universe are causally disconnected and stop this. And this difference in the is the source, is the origin that we see in the cosmic microwave. Once perturbation goes, this value is freezed, remaining history of the universe. At some point, re-enter the horizon because inflation and the universe growing like in a normal way, so the horizon will grow faster than the universe. This wavelength, this re-enter the horizon, and they re-enter the horizon is see them because they re-enter on contact. Why this is important? How this is connected with surface, or how because there is our earlier moment that we can observe, because it's the where photon interact and observe exactly the horizon at the moment, because if you re-enter, you are not in time to re-enter. When you re-enter, the photons stop interacting, so photons are not interacting. If then you undergo plasma, and so this fluctuation, hoping to see they get with all the plasma. So I try to go a bit. I don't know if it's all this information.
Yeah, this is a super complicated topic. So explaining all of this is like a whole one-term long course in cosmology to understand all of this. So just bringing it all back together here, this field that causes inflation, which we call phi, it is a field. It has fluctuations. This is the nature of quantum fields. They will have fluctuations. In the early universe, you have these fluctuations, which we call perturbations. These have an associated wavelength. Now, in the very early universe, these are what we call sub-horizon, which means they oscillate so quickly that they basically oscillate a lot of times within the horizon. Therefore, they don't have a big impact. As the universe expands exponentially, these wavelengths are going to grow, and then they get frozen out when you have this horizon crossing, when the horizons switch around. Later, at the point they're frozen out, their information is locked at this point. This is the state of the system. The wavelength has been frozen. Then these re-enter the horizon, because once you stop growing exponentially, then the normal horizon can catch up. At this point, the perturbations re-enter, and they do so, and they leave an imprint at the time when the photons are still interacting. So these early perturbations, these fluctuations in the very early universe, freeze out, come back into the universe, and when they do, they set the initial conditions of the photons that give rise to the CMB. So, bringing it together, we can use inflation to explain the origin of these tiny, 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 tiny temperature differences on the CMB. So, inflation explains why the CMB has an overall uniform temperature, and at the same time, why it has these tiny temperature differences, why it is not completely uniform. Which is really cool when you think about it, because we can use inflation to tell a story from these quantum fluctuations in the early universe to the patches we see in the cosmic microwave background. So this is really cool when you think about it, right? That we go from quantum fluctuations in the early universe to this amazing cosmic microwave background that we see today. It's really, really cool to think about this whole picture. So inflation solves the horizon problem, solves the flatness problem, solves the monopole problem, and for free gives us an explanation of the origin of the perturbations of the CMB, which is kind of cool when you think about it. So hopefully that was clear to everyone. I know we just dumped a lot of information on you. You know, we just basically summarized an entire cosmology course in 1 hour without using equations, which is not easy to do. So hopefully this picture is clear to you, because it is really, really cool when you think about this. And as always, keep your questions coming. So because we have already gone over the 1 hour mark, Lorenzo, is there anything else you want to tell us about inflation? And also, let me throw in two questions here. Is there anything else you want to tell us? And have we actually found proof of inflation? I'm throwing both of these questions at you.
I would like more because I think that's to start out inflation, how inflation works. So many interesting kind of particular thing, because you be very precise, you a specific amount of energy you went, and it went in a certain way because, for example, a lot of things. So I think maybe it can be a topic, but I leave here for this topic. And how to inflation, was this the next? For what concerns me, there are different the CMB. You can use from the CMB to measure the but what astonishing be in future to detect from inflation. This is what smoking gun, because more than anything, addiction perturbations are exotic perturbations, and this prediction for quantum gravitational in the source of gravity, there's no matter source to them. There are actual predictions. If we really discover ways, cosmological gravitation, that will be inflation exists and exists or it worked way. So I think that is the source that we should look at.
Yeah, so I think that's obviously something really nice to mention, because we have talked a lot about gravitational waves on this show. I've had a lot of people from the group on by now talking about gravitational waves. So just want to go back to something that I was saying here, like, have we found proof of inflation? Now, this is something that, inflation is a model that we have, but it's very hard to try and find stuff about inflation, because as we said with this initial picture of the expansion of the universe, it happened a very long time ago, which means it's very difficult to find any clear evidence for it. Some people argue that the fact that we've observed these perturbations in the CMB is a prediction of inflation, which is true, but also it's also more of a post-diction because we'd already observed these and then we had the explanation for inflation. So you can't really consider that of like a prediction that came true. However, as Lord Lindsay was just saying, we could have these gravitational waves. So inflation is a dramatic process that would probably produce gravitational waves. And if we can measure these gravitational waves coming from inflation, it would be a clear signal that yes, inflation did indeed happen. And that is what a bunch of us work on, trying to find these gravitational waves. Go ahead.
A second, so I thought you were stopped at the source, which is this moment that inflation are. I don't know if the audience, somebody in the audience, have heard of that. Since inflation fluctuations, it might be energy and the temperature to be the seed formation of black holes. There are studies on this because you cannot create a large amount of black holes. Detect some primordial for inflation based on for generation of perturbation.
Yeah, so I think that's also a very good point to make. I was just distracted reading a comment, but yeah, I think that's a very good point to make as well. So we also had a question here from David Howden of could inflation happen again, and do we know if there was only one period of it? And I love those questions because the answer to both is we don't know. Now it could be that inflation. Some people believe in like double inflation or fun things called like waterfall inflation or hybrid inflation, because we haven't yet found clear evidence, like we haven't found proof of inflation or a clear sign of inflation. You can come up with a lot of models, a lot of ways how inflation could have happened. And we didn't have time to go into slow roll and stuff like that, but there are a lot of models of inflation. Now, a lot of them predict a high amount of gravitational waves to the point that we already would have seen these in the way the photons of the CMB move. So based on the fact that we haven't found any gravitational waves imprinted on the CMB yet, we can exclude a lot of models of inflation, but not all of them. So there are still some that work. This is what we do. We roll out the models and until we're left with some. So inflation, we don't know how long it lasted. We don't know if there was several periods of inflation. We know there was at least one. Now, if you have a big gap in between different periods of inflation, then it would affect what you observe. So if there were multiple periods of inflation, they had to be close together. Could it happen again? Maybe. Some people are actually asking the question of is the current accelerated expansion that is being produced by dark energy in any way similar to inflation? It's quite hard to link the two together because of the energy at which they take place. But because we don't yet know exactly what caused inflation, it's quite hard to answer that question. But we don't expect it to happen today, for the main reason that the energy in the universe today is a lot lower than the energy that was around when we triggered inflation the first time. So just on the energy scales, it's quite hard to happen. And we have a comment here from Hemza that basically, we need to see inflation in order to confirm inflation, and that is true. We have a lot of reasons to believe that inflation is a good model, but it might not be the perfect model because we haven't yet found gravitational waves coming from inflation, and we haven't found something we can point to that you say, like, here is a clear thing that shows that inflation must have happened. It is the best model we have, but of course it is not perfect. And a comment from James here, which I'm going to answer very quickly because we've been on for quite a while now. Would a rip in space-time cause an event that mimics Big Bang? And I would ask you there, James, how would you produce a rip in space-time? Because ripping space-time is not particularly easy. We like to use this analogy of a fabric that moves, but this is just an analogy. And when you start trying to rip holes in the fabric of space-time, things get very complicated. So going to put a pin in that question until we figured out how to rip space-time and what that would mean. Okay, so it took us an hour and 15 minutes to get to where we are now, but inflation is a big topic. We even skipped some of what we were planning on saying. So before wrapping up today, Lorenzo, is there anything else you want to mention? Not necessarily about inflation, like about your research, about something else. Like, what are you excited about? What do you want us to know? Like, one thing that you want everyone to know before we wrap up. And I never want. Yeah, I never warn people about this question. Yeah, I don't warn you because then I get a real answer of like, oh, I just thought of this random thing.
Primordial black hole. Primordial black holes, besides being proof of inflation, they are also alternative to dark matter. Primordial black holes, if you detect they exist, they will be very time. They explain two problems. Inflation. Well, they don't. They are big for favor inflation. Solve the problem of dark matter topic in other talks, but this is another cosmology. So I really like the idea of both because black holes they could be very useful. I suggest I look for them. The hopes are not on them, but the idea.
Yeah, primordial black holes are really, really cool. As Lorenz was just saying, they are predicted by many inflationary models, and some models of primordial black holes could solve dark matter. Some people would contest that and say that primordial black holes can't be all of the dark matter, but that's a contentious hot topic. And in fact, we should probably do a whole stream about primordial black holes at some point because there is a lot to unpack there. But for now, we have been online for 1 hour and 20 minutes. So it is definitely time to wrap up this stream. So a huge thanks to you, Lorenzo, for joining today, completely spontaneously, because we only agreed on this on Tuesday. Yeah, it was great to have you on last minute. Really fun. As always, thank you to everyone in the audience for all of the super cool questions and all of the amazing conversation here. It's always great to see everybody. If you haven't done so already, please do like the stream, click the subscribe button, leave a comment. It really, really does help build up the community and build up the network. And I am really seeing a huge amount of an increase in viewership over the last few weeks. So I really appreciate everyone who's helping me increase the viewership of Cup of Cosmology. So thank you everyone for that. Cup of Cosmology should be back online next Sunday, same time as usual, with the comment that some people are going to be doing a time zone shift next week because of the end of daylight saving time, whereas other people will not be. So be sure to check the time zone. It is always 7 p.m. in Europe. So wherever you are, I will tweet about it as always, but check the time next week. Don't miss it because some of us will be changing clocks next week. Nice to hear about non-monetary inflation. Yeah, we definitely didn't choose this topic to get like, oh, inflation. So non-monetary inflation. So again, big thanks to you, Lorenzo, for joining, and thank you everyone in the comments. I hope to see everyone again next week. And in the meantime, everybody stay safe and take care of each other.